So, dear participants, our next speaker is Dr. Shivram Dubey, sir. Dr. Shivram Dubey, sir, has been with Indian Institute of Information Technology, IIIT Allahabad since July 2021, where he is currently the Assistant Professor of Information Technology. He was with the Indian Institute of Information Technology, IIIT Sri City, as Assistant Professor from December 2016 to July 2021, and Research Scientist from June 2016 to December 2016. He received the PhD degree in Computer Vision and Image Processing from Indian Institute of Information Technology, Allahabad in 2016. Before that, from August 2012 to February 2013, he was a project officer in the Computer Science and Engineering Department and Indian Institute of Information Technology, IIIT Madras. Sir, please, sir, over to you, sir.
Okay, thank you very much, Satya. So, a very good afternoon to everyone present over here. So, I hope it is audible.
Yes, sir.
Okay, so I have shared the screen. So, this IIIT Allahabad is one of the Indian Institute of Information Technology, and currently I am affiliated to Computer Vision and Biometrics Lab, and we are having some of the projects ongoing, like this Indo-Taiwan project, which was started when I was there in Sri City itself, and a new project has been also started, which is funded by IDPT Hub Foundation of IIT BHU. So our lab is very dynamic in terms of organization of different activities like short-term courses or conferences, and we are going to organize the third version of CBMI conference, which is International Conference on Computer Vision and Machine Intelligence in 2014. So call for paper is already up for this particular conference, and the proceedings of this conference will be published by IEEE, and this conference is going to be even financially sponsored by IEEE. So its name itself will be IEEE Conference on Computer Vision and Machine Intelligence. So if anyone is having some basic research outcomes and would like to publish, then even they can think of this particular venue to submit their research outcomes. So this particular session is focused on object detection, especially using convolutional neural network. So we can see if we are having an image and we want to find out uh, we want to recognize the objects. So one way we can perform is to classify the entire image into one of the categories. But such type of setup has its limitation. So we, for example, we can only accommodate a single type of object there. If there are multiple type of objects in the same image, then giving a single label to that image is not justifiable. So in that case, it is an obvious solution to first find out or first localize the objects and then find the category of all these objects individually. So that's where localization and detection comes into the picture. So a very basic approach that we can think of to perform the object detection is to just perform a sliding window based approach, where we can just take a window and then we can see is there any object present in that window or not. Even it can be a classical approach or it can be a CNN based approach, but such approaches are having some problem that we will see shortly. What are the major drawbacks of such approaches? However, in general, if we see the challenges in object detection, so there are many challenges. For example, it is possible that the similar type of object might be appearing in completely different appearance, and we can have lot of variations for the same classes. For example, here we can see there are many cars, but the shape of the cars might be different, the viewpoint from where the pictures are taken might be different, the illumination conditions might be different, and even there might be some occlusion also. For example, some person might be behind some car. So there are several such type of challenges which are present especially in object detection. And when we say object detection, then majorly we are interested to find out a bounding box for that particular object. So how we can find out the bounding box, that we will see. And suppose if we have somehow, if we have figured out that this is the bounding box for any object, is it possible to measure the performance? Because if we see the performance measure for basic problems like classification, then we can simply go for accuracy. But if we go for the detection, if we are having a detection problem, then how we can measure the performance of such type of problems? So for example, here we can see, uh, suppose in this picture we are having two objects, one is dog, another one is cat, and ground truth is given to us. So ground truth means we have a bounding box that can serve as the basic template for us, and we can consider this as a reference when we are going to learn our model, or when we are going to evaluate the performance of our model. So at test time, we can predict the bounding boxes, and then we can give the class label as well as confidence score for the object which is contained by that bounding box. So for example, here, suppose at the test time, we got this one as the bounding box, which says that, okay, this is cat and the confidence score is 0.8. Similarly, this is another bounding box detected, which says this is dog. So it is quite possible that bounding box that our model is detecting might not be exactly same as the bounding box of our ground truth. So that's where we have to find out the error, means how our bounding box, which is detected by the model, differing from the ground truth bounding boxes. So how we can measure this particular error in the bounding boxes. So it is also possible we can get multiple bounding boxes detected for the same object with different coordinate as well as different confidence score. So usually for each detection, how what we do to determine is it is a true or false positive. So how we can determine? So there is a Pascal criteria. What that Pascal criteria says that if we take the area of intersection and then divide it by area of union, and if this ratio of area of intersection and division is greater than 0.5, it means that both the bounding boxes are having enough overlap. So this score will be computed between the detected bounding box and the ground truth bounding box. So it is also possible that now we can get even multiple true positives for the same object. So in that particular case, we can perform some non-maxima separation where we can consider that particular bounding box which can have the higher confidence score as compared to the bounding box which is having a smaller confidence score. Or even we can mix the criteria of what is the ratio of this area of intersection and union as well as confidence score. By utilizing both the criteria, non-maximum separation can be performed. So for each class, we find out the detections from highest to lowest confidence and then plot a recall precision curve and then compute the average precision. So that's what is usually computed when we perform the detection. So precision is computed as true positive detections divided by total number of detections, means how many bounding boxes our model is detecting. Out of that, how many are actually correct. So that is the true positive detections divided by total detections. Recall is true positive detections divided by total positive test instances, means how many total bounding boxes are there in our ground truth. Out of that, how many are actually detected. So that's what will be the recall in this particular scenario. So based on precision and recall, even we can have the precision versus recall plot. And what we want here, we want precision and recall both to be at higher side. So we want our curve basically to go towards this right and top corner. So if we take the mean of all average precision, means over all the classes, then we will get mean average precision. So usually MAP is the performance metric used for the detection task. So there are some data sets, for example, Pascal VOC challenge. This was one of the earlier data set which was very popular uh, for example, from 2005 to 12, people are still using, but nowadays Coco is more famous. So this data set was having 20 classes, and data set size was by 2012 11.5k training and validation images and 27k bounding boxes. This data set was also used for segmentation problems, so it also had 7k segmentations. And if we see the progress on this data set, so we can find before CNN, means up to 2012, this mean average precision was somewhere close to 40%. But after CNN, there was huge performance gain in terms of MAP for detection on Pascal VOC dataset. And basically, it shows that convolutional neural network outperformed the traditional methods for the detection problem. So that's where we will see some of the popular CNN-based methods for object detection. The current benchmark is COCO. So COCO dataset is a larger dataset. It has 1.5 million object instances. This dataset is used for multiple purposes for object detection, segmentation, and even it is used for captioning also, because it has some captions, 5 captions per image. So however, here we will only concern to the object detection. So as earlier we have just seen that there could be an approach of the sliding window based approach. So where we can have a window and we can just slide it over the entire spatial resolution, and then at every location we can find out that is there any object present or not. So we can do first a binary classification, object is present or not, and once we figure out object is present, then we can go for the finding its category. So slide a window across the image and then evaluate any detection model at each location to say that there is an object present or not. So major problem, there could be many window that we might be evaluating here or we might be processing. So ultimately this is not going to be an efficient solution, though it is going to be a working solution. We will get the bounding box detected, but it will take a lot of computations as well as uh, number of bounding boxes that we are processing. We have to process many number of bounding boxes, and that too, if you want to extend it to the large range of scales and aspect ratios, means if we change the bounding box sizes as well as aspect ratio, then we have to repeat the same process multiple times. Then again, it is going to be a time consuming process. So then what people do, instead of considering all the bounding boxes, even we can consider some of the probable bounding boxes. Probable bounding boxes means the bounding boxes where the probability of having any object is higher. So then we can utilize some different methods to get the candidate boxes, and once we found the candidate boxes, then we can perform the categorization and we can look for the object only to those bounding boxes which are the candidate boxes. So if we are going for an exhaustive search, if we are going to take the bounding boxes at every location, then we will have many number of bounding boxes as compared to the candidate boxes, which can be in the range of thousands. So a selective search mechanism is very common uh, for finding out the probable bounding boxes. I'm not going in very detail for this work, but it basically makes use of the support vector machine with histogram intersection kernel to find out these probable bounding boxes. And once we have these probable bounding boxes or candidate bounding boxes, then it can be utilized with the models like convolutional neural network that we will see shortly. So if we see approaches to detection, then in early days, like up to uh, 2012, it was dominated by the sliding window based approach. Uh, After that, the methods, especially the convolutional neural network based methods, the proposal driven approaches came here, which was also combined with the deep learning approaches. But then people found that such approaches where we first get the probable bounding boxes and then utilize those probable bounding boxes for the detection, it becomes two-step process. And uh, again, the problem with such approaches in terms of the efficiency. Hello. I hope now it is okay.
Yes, sir.
Okay, fine. So in the first approach, we can just think of utilizing convolutional neural network as a feature extractor to perform the object detection in a sliding window based manner. So where we can have a window and then we can slide over the entire region, and then we, after that, we crop that region and then pass the cropped region to a trained convolutional neural network. So for example, here if we have the window, if the majority portion within the window belongs to background, then the detected category will be a background. So in that case, we need to fine tune any trained CNN model with one additional class, which is the background class, such that the model should give us the detected category if there is any object present. Otherwise, it should classify as a background. So suppose if there is some object here, then it will simply give us the detected class for that particular object. So it means that it will be treated just a classification problem, but entire, instead of giving the entire image as the input to the CNN, the regions will be given as the input to the CNN. So the only problem that we talked about is the efficiency here. And if even if we take an example, suppose if we have 600 cross 600 image and there is sliding window size 20 cross 20, then the number of window that we would be processing is 3,30,000 number of window. And processing one window will take same number of operation as processing one image, because the model that we might be utilizing, that model might be trained on some larger data set for the image classification. So it means that that model would be requiring the images of higher size like 224 cross 224. So our cropped region will be rescaled into that size, and then we can give that cropped region as the input. So it means that processing one image will be equivalent here as the processing 3,30,000 number of images by at the test time. And that too, if we want multiple window size, then it is going to be multiplied with that many number of window size. So ultimately the number of window that we might be processing, it can be in millions. And if you are going to process the millions of window for one image, for testing one image, then it will become very slow. So that's what is one of the problem with this convolutional neural network based approach with sliding window concept. So that's where the reason proposal method of this selective search algorithm is utilized along with CNN, and that method is called RCNN, which was proposed in 2014. So that is reason proposal based convolutional neural network. So RCNN is different from RNN. RNN is recurrent neural network, which is utilized for processing the sequential data, but RCNN stands for reason proposal based convolutional neural network. So in this approach, what happens? The process is exactly similar, but instead of sliding window, we take the candidate boxes, we take the candidate window, and that candidate window will be taken from some another method, which is selective search method. So using selective search method, we find out the candidate window in prior, and which are called the region proposals. Once we have the region proposals, then after that we will crop that and scale as per our requirement of the CNN that we are using. Then these cropped regions and scaled one, means warped image regions, will be given to the convolutional neural network, and each of these window will be processed independently here. So at the end, there is a support vector machine which is used on the top of the convolutional neural network, which will perform the classification using support vector machine. So the idea of this RCNN, we have an input image, we get the region proposals, which might be in the order of some thousands because it is returned by some other algorithm. And then each region proposal will be cropped and given as the input to a CNN. Then the final feature of the CNN will be used by the support vector machine to perform the final classification. So obviously it will be a multi-class support vector machine. So replacing sliding window with a selective search, that is one thing here. Extract rectangles around regions and resize that to 227 cross 227. That depends upon which pre-trained CNN model we are using. So we will take pre-train and then fine tune. So extract features with a fine tuned CNN. So which was initially trained on ImageNet and then fine tuned on this dataset. So classify the last layer of network features with support vector machine and then perform refining of the bounding box. That is there is bounding box regression also. So usually selective search algorithm gives us the number of candidate boxes somewhere close to 1000, means in the order of 1000. Network which was used in the original proposal here was LXNet, which was pre-trained on ImageNet, and then it was fine-tuned on Pascal dataset with 21 classes for classification. Final detector, uh, that is a support vector machine, which takes FC7 feature of this LXNet, and then uh, this support vector machine is trained on that. Performance, which is achieved here, MAP of 53.7% on Pascal 2010, which was much better than selective search algorithm, which gave 35.1% and 33.4%, which was the performance of DPM model, which is DPM model was one of the very famous model uh, before 2012. So there is some advantage of this recurrent, not recurrent, this recent proposal based convolutional neural network based methods. For example, its performance was much better. And another thing is its flexibility to adopt any convolutional neural network. Instead of using LXNet, even we can use any other pre-trained convolutional neural network. But before that, we need to just fine tune it on Pascal dataset for the 21 classes. The downside is this is not a single end-to-end system, means we are not having a complete system where we are just training in one go. So the CNN is trained separately, then fine-tuned separately, then support vector machine is trained separately, and finally regressor is also performed separately. So all these things are done in pieces. So that's why this is not a single end-to-end system. Training was still slow, means it took 24 hours and also a lot of storage, because roughly 2000 CNN passes per image, because still we have order of 1000 number of candidate boxes. So the number of times we are calling CNN is still in the order of 1000 for even a single image. Inference time was also quite slow. For example, 47 seconds taken for one image with VG16 backbone instead of LXNet. Bounding box regression is basically used to fine tune these bounding box coordinates such that we can match with the coordinates that we have for our ground truth. So though RCNN model performance wise, it beats the existing methods of basically non-deep learning based methods, but still there was a concern of efficiency because it was taking a lot of time. And what was the major reason, what is the reason that it is taking the time? Because still we are processing roughly 2000 images for processing a single image, because we are having roughly 2000 number of bounding boxes or order of 1000 number of bounding boxes. But what happens when we have many such bounding boxes, there is a lot of overlap between different bounding boxes, and inherently we are giving those overlapped areas multiple times to the convolutional neural network for processing. And as we know, convolutional neural network has a convolution layer, and that convolution layer has the different kernels. And if we take one kernel, exactly same kernel is used at every location of the image or the input that we have. So it means that when we are having the same kernel to be used on all the bounding boxes that we are providing, and if those bounding boxes are having a lot of overlap areas, then same kernel we are utilizing on the same regions multiple times and doing a lot of redundant task. So that's what was one of the reason why this was still slow, and that reason was pointed out well, and it was incorporated in the next model, which was fast RCNN model, which was proposed in 2015. So in order to get rid of this problem, what the authors have done here, instead of doing the cropping in the image at the image level, the cropping can be performed in the feature space. It means that now the entire image can be given to the convolutional neural network, and then we will perform the cropping at the end of the fifth convolution layer. So in that particular case, what will happen? All the overlap areas that we were doing the processing independently multiple times in the earlier model, now it will be processed in one go. And once we have the final features of the convolution layer, then we will take the cropped features, and then cropped features will be given to the this fully connected layer, followed by the softmax as well as regression. So the entire process now looks like this, that entire image is given to the convolutional neural network, and then we will take the conv5 feature and perform the cropping at the conv5 feature. Obviously, for cropping, we should know the ground truth bounding box information. So at the training time, we know the ground truth bounding box, uh, this one. We also know what is the candidate boxes, because that is given by the selective search algorithm. So those candidate boxes, we can also find out the equivalent candidate boxes in the resolution of the convolution 5, because we know that how image resolution is modified in the feature space, because we know that what are the convolution layers we have, means what are the kernels we have, what is the size of the kernel, what padding we are using, what stride we are using. So based on that, we can also figure out what could be the equivalent bounding box at this particular layer. So that information will be utilized for the cropping of these regions in the feature space. And after cropping, again pooling is performed, and once pooling is done, then this feature is given to the fully connected layers. Each feature will be each features for each regions will be processed independently. So then fully connected layer, the final output of the fully connected layer will be given to the softmax classifier as well as regression. So now in this case, both the classification as well as regression will be performed simultaneously. It means that it can be treated as a multitask, where the log likelihood, means the softmax, which is negative log likelihood, as well as this regression loss like L1 loss, both are combined, and the combined loss is back propagated here, and entire model will become trainable here. Means the back propagation will now start from the final loss, means combined loss, and it will go up to the first layer of this convolutional neural network. So what is the benefit here in terms of training time? Fast RCNN is now taking 9.5 hours as compared to 84 hours of RCNN. So speed up by 8.8 times. And at the test time, speed up is very high. So 146 times speed up is observed using fast RCNN as compared to RCNN. Performance wise, MAP is quite comparable as compared to RCNN. And in fact, it is slightly better than the RCNN. Now, what is the problem with fast RCNN is the selective search method which was being used, which is actually not a deep learning model. That was one of the traditional method, which was based on support vector machine to find out the probable candidate boxes, and it was using the this hand design features to find out such probable bounding boxes. So what another method which also came in 2015. So that method tries to remove this particular aspect of RCNN as well as fast RCNN, where probable candidate boxes are required. So what this model does, which is called faster RCNN, it has a subnetwork. That network is called reason proposal network. That reason proposal network will also take the output of conv5 layer, and then it will generate the probable bounding boxes from that feature. It means that instead of relying on the probable bounding boxes given by some other algorithm, now probable bounding boxes will be computed by this network itself, which is a side network or a sub network of this entire model, which is called RPN or reason proposal network. So the conv5 feature, uh, now again, process is similar to the fast RCNN. The only difference is the entire image is given to the CNN, and we have got the feature conv5 feature. Then conv5 feature is given as the input to result proposal network, and then result proposal network will simply return us the probable bounding boxes. And then using those probable bounding boxes, again we do the cropping of the features of the same conf5 feature and then perform the ROI pooling, and rest of the process is similar to the fast RCNN. But when we say that result proposal network will perform the detection of probable bounding boxes, then obviously this particular subnetwork need to be also trained. Then in order to train this network, there are further losses or the objective functions which will come on this reason proposal network itself. So it means that the features that we are getting for from the reason proposal networks will be passed to the classifier as well as bounding box regression, and this classifier will not do the classification of object categories. It will only do the classification of the having the object and not having the object. Means it will be based on the what is the probability that a particular region might have the object. So how this reason proposal network works, let's have a quick look on that. Suppose we have got the feature map of the last convolution layer here, and once we have the feature map of the last convolution layer, then what we do, again we go with the sliding window based approach. So now we will take a window, and then we will also have some anchor boxes here. So what is the difference between window and anchor boxes? When we say window, then window will have a fixed size, and that window we are going to slide over. If we only work with the window, then we have to do this sliding multiple times. In order to avoid sliding multiple times, this RPN comes with another concept which says that a window will be having multiple anchor boxes, and sliding will happen only once, and then for each of the anchor boxes we will compute the scores. So it means that for the same sliding window, even we can have multiple anchor boxes of multiple, means different size and different aspect ratio. So what we do, we take basically the features which was contained by a particular anchor box, and then that feature is given to the fully connected layer, and then fully connected layer will produce us the objectness classifier, means a score for the classification into binary classes, and bounding box regressor. It means the difference between the ground truth bounding box and this anchor box coordinate. So that difference is basically error. That error is also going to be used into our objective function. That's what is the regression here. So for example, in this case we can see this is the anchor box that we have got, and this one is the ground truth bounding box. So now P object, this 0.94, it means the probability that this anchor box can have an object is 0.94, and at the same time the differences that we will take between the left and top corner coordinates as well as height and width of these bounding boxes will be treated as the error, and that error will be for the regression of the bounding box. Based on that, the bounding boxes can be adjusted. So suppose if our window is here, then this anchor box will give us the objectness score as 0.02. It means that probability is very low, so there might not be any object inside this particular region. So what is the role of multiple anchor boxes? So there is a possibility that we can have lot of different objects in the same image or in different images having different aspect ratio and different sizes. So in order to detect such type of objects of having different appearances, we can go with multiple anchor boxes of different size as well as different aspect ratio or different. So suppose if we are using k anchor boxes, then for each anchor box we will have the different classifiers, we will have the different regression module. So in this particular case, there will be k objectness classifiers. It means we will generate 2k number of scores for the for having the object and not having the object, and also 4k number of this differences in the coordinates as well as their height and width of the bounding boxes. So that's what is being depicted here. So suppose at any particular position where our sliding window is there, means center is that position, Now for different anchor boxes, if we are having k number of anchor boxes, then 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 the feature for each anchor box is mapped to a 256 dimensional vector using a fully connected layer, and then this vector is given to the support vector machine as well as our regression to produce two class scores as well as 4K coordinates here. So now if we see the performance comparison, so as compared to RCNN and fast RCNN, now time requirement is much reduced. So because faster RCNN model is a model where we are not relying on the bounding boxes returned by some other algorithm. So then why, what could be the reason that we are having the better efficiency for faster RCNN? So it is quite possible that when we are detecting the bounding boxes using some other methods, there might be a lot of bounding boxes which are false. But when we perform the RPN here, then there is a quite possibility that the probable bounding boxes that we are referring here, even it might be in terms of order of hundreds. And why it is possible? Because this is based on the data sets that we are using. So in that data set, and because we are also making use of our ground truth bounding boxes, so based on that our model is actually learning. So this RPN module will also learn that what are the objects that we are looking for, and it will only it will try to recommend the bounding boxes which will have the objects that we are interested to detect. Obviously there might be some scenario where such type of appearances can also come if we go in the feature space. So there is a possibility that false bounding boxes might be there, but the number of false bounding boxes that could be there in selective search and that could be there in reason proposal network might be completely different, and here the number of false bounding boxes can be decreased drastically. So that's where the time which is required for the time which is required for faster RCNN model is much lower here, which is 198 millisecond as compared to 2 second for fast RCNN and 50 second for RCNN. And at the same time performance is also improved here, and this is on Pascal datasets of different versions. So these results are reported by is utilizing VGG 16 model as the backbone model, which is pre-trained on ImageNet. So this is the progress on Pascal POC that we have already seen earlier as well. So this is fast RCNN and faster RCNN. So though these models are giving a good performance and also quite effective in terms of the time, but still if you look for real-time applications, then these models still lack, because these are two-step process where in the first step we find out the candidate bounding boxes, and then in the second step we use those candidate bounding boxes to find out the this objects, different objects to be localized in this category. So that's where there are some model which was especially proposed for very fast detection, and one of the such model is you only look once, which is very famous model called YOLO. So in this model what happens, in we don't find out the probable bounding boxes, rather it is just a single stage model where we just give our input image and finally it will produce a tensor as the output. That tensor will have the size 7 cross 7 cross 30. The rest of the things are just a simple convolutional neural network. The Finally, it will produce a vector of 4096, which is remapped to a 7 cross 7 cross 30 tensor. Now, how this tensor is used with respect to our ground truth data to compute the loss, based on that, these outputs will have its significance. So, this 7 cross 7 cross 30, this is actually used in the form of 7 cross 7 cross 5 into B plus C, where this 7 cross 7 is actually treated as a 7 cross 7 grid here, and then for each of the cell this 5 cross B into C. So B is basically the base boxes to a final box with 5 numbers. So basically, how many number of bounding boxes we are utilizing here, along with and for each bounding box there are 5 numbers. And what are those 5 numbers? Those 5 numbers are related to the regression that we are performing, 4 numbers with respect to the coordinate height and width, as well as confidence. And after that we are having c numbers. So these c numbers are the object categories, c number of different objects that we have. So it means that for each cell we interpret the output of our CNN equivalent of having b number of base boxes. Actually we do not have any base box here, but we consider base box in terms of the objective function. So means what final tensor we have got and how we are using those tensors to compute the final error. So based on that, we assume that this particular this tensor structure that we are getting, what could be the meaning of these different values which are present in that final tensor. So in this for Pascal VOC, the number of classes considered is 20, and in the original model the value of b, which was considered as 2 in the experiment. So if b is 2 and c is 20, so in that particular case the final output will be 7 cross 7 cross 30. So uh, that's what was basically depicted in the original figure of this YOLO model. So what is the advantage of YOLO model? The major advantage is we do not have to rely on the two-stage process where we have to first find out the probable boxes and then perform the rest of the things by utilizing those bounding boxes. But if we do not find out the probable bounding boxes, then in that case there it is possible that now our performance will go down. And why our performance will go down? Because when we go for first computing the probable bounding boxes and then looking for then looking for the features of only those bounding boxes to perform final detection as well as regression. But in this case what happens, we are simply relying, or majorly we are relying on the local features which are in the local proximity of that particular grid, which we are assuming for that particular location in that tensor. So it means that the the utilization of the features which are basically from the different context or different objects, those would be missing in case of the YOLO model as compared to the model that we had for the fast RCNN or even faster RCNN. And at the same time, if the number of b values that we are using here, we are actually not having much control on such b bounding boxes, because how many number of bounding boxes we are using, that is basically defined by the problem that we are solving. Or sometimes we just try to maximize the efficiency, so we reduce the number of bounding boxes. So that's where the possibility of detecting the objects of at very varying scales as well as varying sizes and aspect ratios. So this YOLO model will suffer when we are having such type of scenario. So if we see the performance wise here, so as compared to faster RCNN, roughly 7 times the speed up is observed uh, for using this YOLO. So 45 to 145 frame per second can be processed using YOLO. It means that we can achieve real-time performance as compared to 7 to 18 frame per second, which can be processed using faster RCNN model. Localization accuracy suffers compared to faster RCNN due to coarser features and errors on small boxes that we are having in YOLO, which is better handled in case of the faster RCNN and other models. Other means two-stage based models. Single shot multi-box detector is another single stage model where i- to get rid of the problem of YOLO, the bounding boxes, the features which are considered for final detection, these features are considered from the different scales of this convolutional neural network. So when we consider the features from the different scales, then basically the scaling problems means detecting a different scale of the object, such type of problem is reduced. But at the same time, then the computation will increase. So SSD will YOLO will be much better in terms of efficiency, but at the same time, if you go with the performance wise, then we find SSD will be better as compared to YOLO. So this is a very nice trade-off that we can observe between the performance means accuracy here. Accuracy means actually it is mean average precision. So accuracy and speed. This fast RCNN, if we see, speed is very low and accuracy is fine. And YOLO, if we see, its speed is very high, but accuracy is lower than faster RCNN and SSD. So that's where we can find out a better trade-off. So if we go with a better trade-off, then SSD could be a good choice, which can even have a good speed, but at the same time, good accuracy also. But if we look for real-time performance, then YOLO and different versions of YOLO can be utilized. So YOLO has different versions. We are not going with different versions of YOLO, but right now, at least 8 different versions are already there. And what is the changes in different versions? People are trying to further reduce the number of operations and at the same time to improve the performance. For that, different mechanisms have been utilized. So RetinaNet is one of the model which simply just tries to modify the loss function. So there is no difference at the architecture level. Mask RCNN is also another model which is majorly used for instance segmentation. So YOLO V2, there is V3. The different YOLO versions are there. So basically, if you see these CNN based models are very prominent nowadays for performing the object detection, and there it depends upon what is our requirement. We want performance, means we want much better performance, or we want much better speed. So based on that, we can go with either two-stage models or one-stage models. And nowadays transformers is one of very prominent area which is slowly replacing the convolutional neural network. And transformer is also being utilized for object detection, and a lot of works are coming in. And DETR is one of earlier work of transformer for the detection problem. Okay, so that's it for object detection. Now, if you have any questions related to object detection, you can feel free to ask.
Hello, am I audible, sir?
Yes, Dr. Rakesh.
Sir, one of the participants want to ask a question, sir. Can you please?
Non-maximum separation used in. So it is possible that for the same object, we can get multiple boxes detected. So when we get multiple boxes detected, and all boxes are true positive. True positive, how we decide the true positive? So we will take the area of overlap between the detected box and the ground truth box, and the area of union means intersection divided by union. If it is greater than a threshold, usually threshold is 0.5, uh, then in that case it is true box. So it is possible that we can get even multiple true boxes, because we are having different anchor boxes. So based on that, we can get the multiple these true boxes. So in that case, but ultimately we have to recommend only one box for one object. So we have to pick only one box out of all the true detected boxes. So that's where non-maxima comparison will come into the picture. The usual approach that people follow is to make use of the confidence score. So the bounding box among all true bounding boxes for the same object, we pick which one is having the highest confidence score. However, some even better strategies could be adopted where a trade-off can be seen between uh, the score of this intersection and union as well as the confidence score. Both can be utilized together to pick uh, the bounding box which can be much better representation of that particular object. So Moti Gupta, is it clear to you? Okay, thank you. So there is another question. Some details of variants of YOLO architecture. Yeah, there are several variants, V1, V2, V3, and even V8. So I guess in V3 or V4, this one darknet model was also utilized. So there are plenty of comparative study that people are doing that you may have a look. And the recent YOLO V8 model are also utilizing the transformer, means attention based mechanism, because attention based mechanism is very common nowadays. Which YOLO variants is used when? Okay, so there is no fixed guidelines which YOLO variants is being used when. If you see the research progress, so people are simply running behind the latest methods. So whenever any new YOLO model comes, simply people try to just use those new YOLO models in their problem. So, but still you can look for some research articles where people have performed the performance analysis of different YOLO models for different problems. But usually, YOLO models you can analyze in terms of the efficiency as well as performance. But whenever a new YOLO models are coming, usually we are finding the lighter models with the better performance, then only new versions are usually proposed. Which is the most useful algorithm for instance segmentation? So sometime back it was mask RCNN, which was very popular as well as very effective also for instance segmentation. And nowadays, again, transformer based models are there. You can just search for transformer based models for instance segmentation. You will find it. And basically, it is making use of the vision transformer. How does the annotation system for microscopic images work when there are no classes? How do we go about? But what is the application for this microscopic images? Means you are going for classification or detection or segmentation. So based on that, annotation need to be performed. So there are many microscopic data sets where different categories are there. Means just one category for one image. But majority of the applications where people uses medical images, segmentation problem is very common. So for segmentation problem, now we can have a ground truth, means annotation. That annotation will have the basically class labels for every pixel, which can be also treated as the segmentation map. Then the class label can be mapped with different color maps. So when we visualize the segmentation map, then we get the color maps instead of class label, because every class label is just coded to a color. So in visualization we get the colors, but actually we are having different class labels. So segmentation problem is also performed in two ways. Either we can go with the pixel wise classification, or we can go with the generative model. So in generative models, we will go with the holistic view, but there also we can go with pixel level errors if it is a paired problem. But if it is a not non-paired problem, suppose in your data set if registration is not done properly, then we need to go with unpaired scenario. So there we cannot go with any pixel level error function. Okay, any specific scenario, if you are there in your mind, then you can just mention it here.
Hello, sir.
Yes, yes.
I'm one of the offline student attending this workshop. I had one question related to evaluation metrics. Like one is usually here is like MAP we are using for object detection, right?
Yes, yes.
That will be coming from the precision and recall, and precision will be coming from the true positives and the confusion matrix.
Precision will come from the precision is basically the ratio of the detected regions which are true divided by the total number of detected regions. It means that true positive divided by true positive plus false positive.
Yeah, but in normal classification, the true positives is like you're having a positive class and truly predicted. But in the context of object detection, you're also adding this IO threshold as one of the criterion, like to divide between a false positive and also true positive.
Yes, yes. So true positive and false positive will be decided by the intersection over union.
Okay. Will there be true negative and false negatives also for this object detection in one class when there is a scenario of only one class?
When there is a scenario of only one class.
Yeah.
So even if you have one class, but still you can get the false positives. Means it is possible that some of the objects in your background can be detected as the object for your class. So in that case, it will become false positive.
Yeah, false positive is there, true positive is there, but will there be what is true negative and what is false negative in this object detection?
So in object detection, the performance metric that we are using, suppose precision that we are using. So there we are not interested about the this true negative. Okay. So in that performance metric, that part is not there because if you see what is the recall. So recall is the number of uh, true detected regions divide means boxes divided by the total number of bounding boxes that we have in our ground truth.
Okay. Um, and can you point out me can you give me input about suggestions of some models which are useful for the small object detection? So I want to detect small objects in an image or something.
Yes, yes. So there are many tiny detection models are there. So in tiny detection model, what those models do, they utilizes the CNN and they utilizes the CNN in a hierarchical fashion where they also reduce the resolution of the images and then perform the detections. So basically, the detection is being performed at different resolutions. That different resolutions that we are getting, we get from the feature space also, and we get from the image space also. So when we perform this particular task, and because this is being learned in a supervised fashion, so for our ground truth also, we reduce the resolution and also we reduce the bounding boxes sizes. So basically, the image that we have now, we can train our model at different resolutions, even with a very smaller resolutions. So there we can do this tiny object detection.
Yeah, okay, that approach is nice, but are there any open source models following that approach?
Yes, yes, there are many models are available, and even tiny face is one of the model which perform the face detection even in the crowded scenario where we are having very small faces.
Okay. And they were saying the last slide is about the detection transform DETR. Um,
Yes.
one thing, in YOLO, you're getting the bonding box and you're doing a post processing step, which is like non-max suppression. Um, in this DETR, is there any thing which we need to handle these multiple bonding box being predicted, like NMS, or is that any handled in the model itself, or we have to do another post processing step?
In case of the DETR,
Yeah.
in case of the DETR model uses the encoder. Encoder output is given to a FFN, which will give us the class score and bounding boxes. Yes, because it also gives us the multiple classes, right? So it means that how many number of outputs we are considering for our decoder. Each output can give us one class. So then it is possible that means this bounding boxes as well as class, then there is a possibility that we can get the multiple bounding boxes. Yes, then non-maxima can be applied.
Okay. Okay, so thank
Okay, thank you very much. So there are some more questions here. Will there be coding sessions on object detection using YOLO faster RCN in this workshop? Okay, that you may ask from Dr. Rakesh later on. If there are two classes which looks almost similar in image detection, how to approach this scenario? Okay, so there are instance segmentations. Instance segmentation is able to perform this. Even in object detection also it can be performed, even if they are similar. Means detection wise there is no problem. You will be able to detect the those bounding boxes for all such instances. But when how your recognition model is working, you need to check for that. So in that particular case, what you can do if they are very similar, so instead of only relying on the losses like softmax loss, you can also go for some pairwise losses, means similarity or dissimilarity losses, which are basically like siamese or other type of losses can be also utilized. So if you see face recognition approaches, so most of the face recognition models, they try to utilize the objective functions based on the similarity between the faces in the feature space. However, if you see the cross entropy, they are mostly based on the class scores for the different classes. So when similarity is very high between different categories, then we can utilize the cross entropy. Apart from that, we can also go for some other losses like this Siamese based losses or triplet losses, and that will give you better discrimination in the feature space as compared to only softmax. Can you discuss about how to improve intuition regarding developing better loss functions for different tasks, especially when have less data? Okay, when you have less data, then transfer learning is one of the approach that people are following. And as I just mentioned, if you are having less data, then uh, uh, usually objective functions depends upon not only the data but the problem that you are solving. So for example, if you are going for classification, then this cross entropy is the major loss, but now you can find different variants of cross entropy. And if you go with the different variants, then what people are trying to do, is it possible that we can give more weightage to the hard examples? Some your samples can be divided in different types of examples: hard examples, easy examples, and average examples. So based on that, some modifications can be done in the uh, objective functions. Similarly, if we go for the object detection, so in object detection, I did not discuss this retina in very detail, but the purpose of that retina net was the same thing. Means whenever we are performing the detection, so most of the time what we are finding, we are able to detect most of uh, we are able to detect most of the easy examples very easily. But when we go for the detection of hard examples, then that detection is actually fails. But when we take the uh, objective function, then objective function is basically the average over the error of all the instances that we have. So in that case, when you are having majority of the bounding boxes being detected correctly, then if you take the average of the performance, then in average we will not have much representation of the hard examples. So that's what this retina net also tries to do. So it basically decreases the weight of such examples where we are able to detect the bounding boxes very easily. But at the same time, where we are failing, the weight for that will automatically increase in that uh, objective function. So this is, there is no just one specific way to do that. This is, there are multiple ways uh, where objective functions can be utilized in a better way to solve different problems. Okay, so Dr. Rakesh, so should we start the next topic, or is there any break that you are going to have?
I think you may start, sir, because we don't have a time.
Okay, so next topic, what I will do, I will give more uh, time only to the basics.
Yes,
Rest of the things I will go quickly.
yes, yes, yes. You may start, sir.
Okay, so another topic that I'm going to quickly cover is self-supervised learning, which is one of very interesting topic and very recent topics. And first of all, let's try to see the motivation behind this, why uh, this self-supervised learning is useful. So broadly, if you see, we divide these classification problems into supervised and unsupervised problems. Not just classification, any machine learning problem we divide into supervised and unsupervised. When we say supervised, it means that at the training time, we are having ground truth data, and then we make use of that ground truth data at the training time to train our model. But when we say unsupervised, then unsupervised means we do not have any ground truth data available with us. So a very pure unsupervised problem, if you see, then clustering is one of very pure unsupervised problem where we are only have the data, we do not have any ground truth, and we want to divide that data into certain categories. So that's where these clustering algorithms comes into the picture. So unsupervised learning is very, very important. Why it is important? Because if we go for real scenario, then many time it is not feasible to get the annotated data for our model to get trained. And training and annotation many times becomes very manual work, and lot of time and efforts, as well as this many resources are required to perform the labeling of the large scale data set. So that's where this unsupervised learning comes into the picture. But when we go with pure unsupervised learning problem, then also we find a lot of bottlenecks, that what are different things that we can do in unsupervised learning. So in unsupervised learning, we can look for basically clustering. We can also try to perform something like self-supervised learning, where we can convert the super unsupervised learning problem into a supervised learning problem, but not with any ground truth data, but generated ground truth data. It means that from the data we can do some transformation, and from that transformation we can generate the data as well as ground truth both. For that, any manual annotation is not required, that can be done in an automated way. And in that particular scenario, we can train our model by using the generated data as well as generated ground truth, and that's what is the self supervised. So when we perform the self supervised, then obviously the generation means the transformations that we are doing, those transformations might be limited to some of the transformations. It means that the ground truth that we are creating, that ground truth might not be directly related to the problem that we want to actually solve. So that's where the self supervised whatever processing we will do for the self-supervised model that can be treated as a pre-processing part here, and then the actual problem that we are solving can be treated as a downstream task. So now we are basically we are going to set our model based on the self-supervised, and then we will use those trained model for any downstream task. So then what is the purpose of using this self-supervised here? The main purpose of the self-supervised is
You're
to,
not presenting. The screen is not visible.
oh, sorry. Okay, I hope now it is visible. So is it visible now? Or is still not?
Yes, yes, sir. Visible.
Okay, fine. So so what is the major bottleneck of supervised learning is to have the annotated data, and in order to get the annotated data, a lot of manual work is required. So that's where, in order to train very large scale models, we can uh, or even the models where we are getting the scenario where we are getting the data continuously, it is very difficult to have the annotated data. In such scenario, we can go with the unsupervised learning. And in unsupervised learning, basically we go with the self-supervised, which is one of the uh, form of the unsupervised learning. Because in case of the self-supervised, we do not need any ground truth data from our user. So that ground truth will be generated at the training time itself by the program. Okay, then what this self-supervised learning do? Uh, it basically makes up the labels from the data itself, and then treat the problem as a supervised problem. But it might not be solving the actual problem that we want to solve. Then what is the purpose of self-supervision? The purpose of the self-supervision is to learn the representation of the image, means the common objects, the common scenarios which might be present in most of the different type of images. The representation of such type of objects and scenarios can be learned, and then from that representation we can do the fine tuning for any other task that we want to actually solve. Unsupervised learning, any kind of learning without labels, means there is no label at all given to us. So for example, clustering or quantization, dimensionality reduction, manifold learning, density estimation, even learning to sample, like you have already seen generative adversarial network. So all such type of applications are pure unsupervised learning. So in order to boost the performance of unsupervised learning, now the self supervised learning can be one of the additional step here. So there are different types of self supervised learning. The one type is data prediction. In case of the data prediction, what happens, we have a network. That network will try to basically modify the data x into data x dash, and then we want to predict that. Transformation prediction. In the transformation prediction, we want to predict which transformation is used to transform the data. Contrastive learning. So in contrastive learning, again, we try to learn the similarity and dissimilarity between different view of the data. So what is meaning of different view is different transformed versions. So in data prediction, some of the methods like colorization, super resolution, inpainting, cross-channel encoding is used. Transformation prediction, context prediction, jigsaw puzzle solving, rotation prediction. Automatic label generation, image clustering can be utilized. Contrastive learning, like we have this PIRL, which is pre-trained, MOCO, CMCLR, this swapping SWAV. So there are such different models are available. Nowadays, if you see in recent days, this contrastive learning based self-supervision is very famous, and it is being utilized in almost all the transformer models. And if you see, the transformer models are able to give very good performance like GPT and all, because they are actually heavily relying on the self-supervised learning. So now let's quickly have a look what is meaning of these different methods here. So because generative adversarial network, so these things are very simple to you. So in case of the data prediction, so we can have the colorization, super resolution, inpainting, cross-channel encoding. It means that we can perform any sort of operation where image can be transformed into some other image, and the transformation that we are utilizing, such transformation can be utilized directly at the training time, and then data can be transformed. So it means what? From x we can produce x dash, and then we can try to find out x from the x dash. So conversion from x to x dash is manual, and then conversion back x dash to x, that's what is basically uh, the self supervision. That's where because when we are generating from x to x dash manually, then we know that x dash is corresponding to x. It means now we are having the ground truth information. So it means suppose if we want to perform the colorization, so we do not have any ground truth, but at the same time if we have an color image, then we can generate the grayscale image corresponding to that color image. That is the manual process that we apply. So it means that now we can have the ground truth also and input also. In this case, now we can give the grayscale version as the input to our model, and then from model we try to predict or try to generate the colored version, and then the original color image is also available with us, because that's what was our actual input from where we generated the grayscale image as the input for our self supervision. So now in this case, if you see, for image colorization problem, we do not need the grayscale images, original grayscale images. Rather, we can generate grayscale images from color image itself. So that's where the original ground truth information is not required here, and the ground truth can be just created at the training time itself. So at the training time, we are having the color images. Then what we do, we generate the grayscale images of those color images manually, and then grayscale version will be given as the input, and then we try to predict the color version. There are several models that can be utilized for the color, means backbone models which can be utilized, and then that backbone model will be trained. This is just ambiguity. So obviously we can get different output for the same grayscale. It is quite possible. Super resolution. For super resolution also, it is possible to create the ground truth from our data itself. Suppose we are having the samples, we can just reduce the size of the sample by downsampling. Any existing method can be used to perform the downsampling, and then downsampled version can be given as the input to our model, and then we try to perform the super resolution, and then n- now the original image will be also available with us as the ground truth, because that's what will be our actual super resolution, means high resolution image. So such type of translation, this is also kind of a translation from is low resolution to high resolution. So such type of translation can be also done using the GAN based models, where our generator can take a low resolution and then it can give us high resolution output. Then we can have the losses between high resolution, generated high resolution, and the actual high resolution. And because the low resolution we are generating from the actual high resolution itself, so that's where even we can go with any pixel level loss here in this case. So this L2 plus content loss is the pixel level loss. Apart from that, we can have the generative, means adversarial loss as well, that is generator and discriminator loss. Similarly for inpainting also, in case of inpainting, we keep the same resolution, but now we can insert now we can insert mask anywhere in the image in the random fashion, random size, and random color. Even we can have the texture of the textured based mask. So such type of things can be included in the image. Then we will basically have these generated images here as the input now, and we will try to construct the original one. So again, this type of problems can be given to the GAN based models. So in GAN based models, now we can train this generator model. The cross channel encoding can be also utilized, where we can basically perform the swapping of different color spaces or color channels, and then we try to find out the correct order. So that can be also performed, and then we can basically train any GAN model, because this is also kind of a application where our input is an image and output is also an image. So suppose if we perform all such type of applications at the training time, if we use all such applications at the training time to train this generator model, so at the end, the encoder of this generator model, because this generator model will have two part, encoder and decoder. So the encoder of the generator model will be trained in such a way that it will be able to convert any given image into feature space, where that feature will be a good representation of these input images. Because when we are saying when we are saying that, okay, do the colorization, in that particular case we are teaching our model how to learn the color consistency between different parts of the object. When we are making use of this SR, the super resolution, then also we are making in that case we are making our generator to learn that how these local information is used, such that when you are going to even increase the size, then those local information will be interpolated to give us the better result. When we are having the image in painting problem, then in that case we are teaching our model to learn the dependency of a particular region with other regions, because that's how it can find out that what was the object actually at this particular location. So inherently what happens by making use of all such applications at the training time, the generator model, especially the encoder of that generator model, is able to learn a better representation of the input images. So suppose and in order to do this training, we do not need any actual label, so we can generate all these labels at the training time. So it means that we can train our generator on a very 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 large scale data set. It means even we can crawl from just internet, we can have a lot of different type of images, and these models just can be trained on a very different type of images, having a lot of variety of different objects as well as scene. So that's where the encoder of this generator will be very powerful in terms of learning the representation. And then such representations can be utilized for other applications. For example, we want to do classification or detection or segmentation, such type of problems. Another way is to predict the transformation. Means instead of finding out the image itself, now we will find out what transformation was actually used to perform the transformation. So let's have a look on the context prediction. So in case of the context prediction, what we do, we take a region and take the surrounding regions, and then if I take any random surrounding regions from here, means any random neighbor, and then if I take that particular patch along with the center patch, then we find out that what was the relative location of that patch. Means this was 1 2 3 4 5 6 7 or 8. So it means that basically we want to find out in which category it should go. So now top left corner will be treated as category 1, top will be treated as category 2, top right corner will be treated as category 3. So it means that now every patch will be given as a class label, and these class labels are actually giving us information about the relative location of that patch with respect to the center patch. And for that also we do not need any ground truth information from the user. Such type of things can be generated by our own using just program, or using just we can just write a simple code to perform this type of sampling and generate a lot of pairs. And from where we are taking at the training time, we will make use of that particular relative location, means corresponding class category. So now these two patches will be utilized together. So these two patches will be given as the input to the model. So for example here, so this is the patch 1 and patch 2. So both are given as the input to any convolutional neural network, and that convolutional neural network will have the shared weights between different patches, and we will get their features. So now we get the feature from the center patch. We also get the feature for the any neighboring patch which is given to us. And after that, by making use of both the features, we are having a small fully connected layer here. That fully connected layer will make use of the features of both the patches, and ultimately it will classify using softmax into one of these 8 categories. So suppose if it is classifying into category number 1, it means that actually it is classifying to the top and left corner. So now if you see, if we are training our model, then at the training time we are giving the class labels. Class labels are based on what is the relative location of this neighboring patch with respect to the center patch. So ultimately, if our model is able to give the correct class, it means that somehow our model is able to figure out the similarity or the relative uh, information between or dependency between the center patch and the corresponding patch. It means actually our model is able to figure out what is the visual appearance of any particular object. That's why it is able to give us the correct relative location of these two patches, which might be part of the same object, or even it might have even some portion coming from some different objects or even background. So that's what is being shown here. So if these two patches are given here, it will show bottom right. Next one is top corner, because if this one is center, then this particular one is going to be this corner, which is bottom and right. So by making use of this, actually we are making this convolutional neural network to learn the interdependencies between different patches of the same of this object. So by using the learned weights of RCNN model to perform detection on Pascal VOC 2007, unsupervised pre-training is 5% MAP better than the training from scratch. Means if we perform training from scratch, then uh, whatever is the performance, we are getting 5% better performance when we do the unsupervised pre-training. But it is still 8% below pre-training with ImageNet level supervision. Means if we go with pure supervised problem, then that performance is 8% better. It means that if we only utilize the context prediction, then the performance is not as par uh, as the supervised problem. So it means uh, just by using context prediction, we cannot match the performance of supervised learning problem. However, we will see that there are other transformations. If we utilize those, then even we can match the performance of supervised learning. Jigsaw puzzle solving, this is another method. So in jigsaw puzzle solving, what we do, this is again based on the interdependency between different neighboring patches. But in this case, what happens, we take the different patches and then shuffle the order of those patches. And then what is our pre-text task? Whatever we are doing using this self-supervision is called pre-text task. And once our self-supervision is finished and we are want to apply to a specific application, then that will become the downstream application. So here our self-supervision mechanism is to reassemble. Reassemble is means finding the correct order. So what is the problem with such a this particular approach? The number of different possible permutations that we can get is very high. So it means if you want to train for this jigsaw puzzle solving, then that many number of classes we need. And working with that many number of classes, that is not going to be very helpful So that's where what is done here. Only 64 only 64 permutations are considered, because even if we consider a permutation and the next permutation with only change of the position of only one patch, then it is not going to be very useful. So that's where 64, it is predetermined set of 100 permutations, not 64. It is 100 permutations are used out of total number of permutations which are possible. So after that, that's where basically we can reduce the number of these classes that we have. So what is the usual process here? We do the shuffling, and after shuffling, we provide each patch to our convolutional neural network. We get the final features. Those features are combined and finally passed to the this softmax here. So by making use of this, again, what we are doing, uh, we are trying to make our model to learn what is the dependency or how different part of the object are related to the other parts of the object. So that's where basically it will be able to learn the holistic representation of that entire object. Means first it will learn part based and then it will be combined in order to have the object level representation. Rotation prediction is another way where we can simply rotate the image, give the rotated version, and then try to find out the rotation category. So suppose if we are having rotation angles as 0, 90, 180, 270. So these are four categories now. And then if we give the rotated version, then we want to classify into the corresponding category. So again, if we are able to yeah, if we are able to find out the correct rotation category, then it means that our model is able to learn that how a particular object looks like, and that's where if that object is rotated, then it is able to find out the rotated angle of that particular object. So here is the performance on Pascal VOC, and this is using transfer results. So pure supervised problem means pure supervised learning for classification 79.9, detection 56.8, segmentation, which is mean IOU 48.0. If we use only colorization, then classification 65.6, one context prediction 65.3, jigsaw puzzle solving 67.6, rotation 73. So then it figures out that the rotation is very powerful pretext task, and using rotation model is able to learn better representation of the object. And similar trend is also followed even for the detection. We also find for segmentation, rotation based pretext is very useful, but is still not matching the result of the this supervised. But in the case of classification 73, which is very near to 79.9, because for using colorization it was only 65.6. Automatic label generation, so clustering can be performed. So using cluster, what can be done? First, images can be divided into different clusters by making use of the CNN feature, and then those clusters can serve as the pseudo labels. So for example, if we are able to divide into some k number of clusters, then for every example means for any example in which cluster it has been divided, we will try to classify into that particular category using the same feature using with softmax. So first we perform the clustering here using this using the final feature of the coordinate. And once clustering is done, so this clustering, any clustering method can be utilized here. Suppose even we can go with k-means clustering or any other clustering methods, or this median based clustering. So using a deep clustering approach, the performance for classification is very similar to the rotation. but for segmentation, this is useful. So now coming to the latest methods here, which is the contrastive learning, and contrastive learning is very, very powerful to learn the representation, because contrastive learning makes use of the similarity, learning of similarity and dissimilarity. So what happens here for again pretext transformation? Uh, so this is in general self-supervised learning pipeline. So we have pretext transformation where we want to find out the representation, and then we can make use of such trained model to perform any other task. In contrastive learning, what we do, we generate different transformed versions of the samples and then learn similarity and dissimilarity. So that's what is being shown here. So now we are having two images, the first image and the second one is the transformed image of the first one. And then, and here we are having another example. And now what we want to do, we want this original image of the original image as well as this transformed version. These images should have the dissimilarity as compared to any other image here. And the different images which are generated by transformations, we want to have the similarity between those images. But obviously, because we do not have any class labels, so how to say that, then how to find out, how to say that these two samples are different, and in this feature space we should have the differences, or basically we try to have their features very, very far from each other. So usually then what is the process? The process is all the images or all the generated sample from a sample will be treated as the positive examples, and we will try to maximize similarity between them. And if we consider any other example from our database, then that example will be treated as a different example, and it will be simply considered as a dissimilar image. Obviously, it is having a drawback. So it is possible that if we are randomly taking any other example from our database, it is possible that another example might also come from the same category. Though we do not have category labels, but it is possible that suppose in our data set we are having multiple cats. So and one cat now we have taken, then from that cat we have generated a lot of different transformed version of the cat. So now all the transformed version of the cat, they are the positive examples for our cat. But we also need some negative examples because we do not have actual class labels, so we cannot figure out the correct negative examples. Then what is the strategy adopted here? The strategy adopted is to randomly take any sample from our database. Now whatever sample we have taken from our database, we consider that sample as the negative sample with respect to this cat. So obviously when we are taking any negative sample, there is a possibility that it is actually negative, it might be having some other object, but there is some possibility that the taken image is also having this also from the same category cat. But such type of possibilities are very less, and that can be considered as noise. In original contrastive method there is no way to get rid of this problem, so still we learn only with this strategy. But there are new methods being investigated nowadays where people try to find out different ways to tackle this particular issue. So if we see the contrastive loss formulation, so for any given input image x, we have the positive samples x plus. These positive samples are nothing but these are generated samples by any transformation that we could apply, very similar to data augmentation. All the transformations that usually we perform for the data augmentation are also utilized to get these positive samples. So in other words, we can say that we are generating different views of the data using data augmentation. Negative samples, as I mentioned, these examples are simply randomly taken from our database. So positives are typically transformed versions and negatives are random examples from the same mini batch or the memory bank that we have. So what is our idea here for contrastive loss? The idea is in the feature space, the feature of x should become very similar to the feature of x plus, means similar positive samples, and feature of x should become far away from the features of negative samples. So that's what is the major uh, objective that we want to achieve here. So for that, contrastive loss is utilized. What is contrastive loss? So this is negative log likelihood of exponential of. So what is what it says? Fx means the feature of that feature is computed from any model. It can be any simple model or CNN model or ANN model. So Fx is the feature of x which is computed by any either uh, parametric or non-parametric model, or even deep learning model, or even transformer based model. Any model can be there. So what we do, we perform the dot product between the feature vector of x and positive samples, and we know that dot product will give us the higher value if those features are aligned with each other. So, and then we take the e to the power of that, because we want to convert everything into the positive domain. So exponential will convert everything into positive, and also it will give better separation of for those alignment scores which are very similar to each other. At downside here we can see we are having again the same term, means alignment score between the positive samples, and then alignment score between the negative samples here. This tau is there, which is called the temperature hyperparameter, and manually its value is set here, and it determines how concentrated is the softmax that basically we are using. So what we will try to do, we want to minimize this. If we want to minimize this loss, then inherently what what it will do, because we are having negative log likelihood, so it means that it will try to maximize the upper term and it will try to minimize this lower term, and lower term has the majority in terms of the negative examples, because that's where we have the summation from 1 to n, because we can have now not just one negative example, we can take n number of negative examples. So inherently if we try to do that, then ultimately it will try to shift uh, the feature vector of the image x uh, away from the feature vector of negative samples, which is xj minus, and at the same time it will try to align the feature vector of x with the feature vector of x plus. So that's where it is basically it is able to learn the representation of our input images. So that's what is called pretext invariant representation learning, exactly same thing that we have just seen here. So our input image and the transformed version both are given as the input, and then we try to minimize the distance between the representation of the input image as well as its transformed version. So PIRL, this is a generic framework, and it makes use of a memory bank. From the memory bank, we take some samples and then we try to find out the similarity and dissimilarity between those samples. So this is having noise contrastive estimator, which is very similar to the this loss that we have just seen. Now if you see the performance here, so PIRL, if we take the average precision here, then 54% for all, and it is also better than the supervised. So supervised is having 52.6, but PIRL gives 54. MOCO is also one of the self-supervised method which gives 55.2%. So MOCO is momentum contrast. So instead of using memory bank, basically it uses a momentum encoder, where uh, basically this xk that we are having, we will have the past record, and whatever the new record is coming, that will replace the older record. So we will kind of a momentum will be updated here, which will be utilized for the contrast loss. So here we can see, so once we are getting different keys, so this momentum encoder will basically maintain a queue of this. So SimCLR, this is one of recent methods. So what it tries to do, instead of trying to find out the similarity between the image and its view, it tries to find the similarity between different views of the same image. Means it does not use the original image, but it uses only different views of the images. swapping assignment between views. So it tries to uh, get the quantized code. So basically quantization is also used when we get the codes here for uh, applications like retrieval application. So it tries to basically find out those codes from the swapped these features that we have from the different views. So that's how it basically learns the similarity between different views. So its performance is also appealing here with 78.5 for ImageNet top 1 accuracy. So there are many such improvements which are being done, and people are also trying to investigate why these contrastive methods working. And as I mentioned, many works are also happening to get rid of this ambiguity where false examples are considered as the negative views. So not just images, I mean it is also utilized for other type of data, like for audio also it is utilized, for video frames also it is utilized. And video frames uh, we can have shuffled order, and then we can try to predict the correct order that can be done. We can also try to find out the future frames. Future frame prediction can be also performed like this one. So self-supervised learning is very happily used in transformer models like BERT or even GPTs. And that's why these models are able to learn the representations from very, very large scale data sets as a pre-text task. And then those representations are fine-tuned for specific applications. Okay, so that's it about this self-supervised learning. So now, if you have any questions, you can feel free to ask. Satya, are you there? So there is a question from Tanusri Roy. Is it possible to use self-supervised learning for numeric data set, not for images? Yes, it is possible to utilize, but the only thing you need to see the kind of data augmentations that you are using for numeric data set. Similar type of augmentations you can use for generating different views, and then you can use the contrastive learn. This contrastive learning means contrastive loss for self-supervised learning. Means as long as any transformation that we are applying, and if it does not change the meaning of that particular sample, so we can utilize it. Okay, so is there any other question from anyone? You can ask, otherwise we will end the session because I think we are already late. Okay, so thank you very much to all the participants as well as organizers for organizing this particular workshop, and all the participants for attending this workshop. So thank you very much, and we can surely meet at some or other places.